is rough. I'm going to release a rigid body on a rough inclined plane. The radius of this, let it be smaller, capital R. This is the center of mass. Let M be the mass. I'm going to release from rest here. Rough inclined plane. Let mu be the quotient of friction. What conditions will arise here? So that let me get into the problem. Mg sine theta. Then how the friction, if no slipping occurs. Then look at this point P, very important. Due to mg sine theta, the center of mass will try to accelerate down. Then for no slipping occurs, R alpha should be upward, R alpha C should be upward. Then only no slipping will occur. So therefore, how the torque, how the friction only can set up that particular torque. Then only open acceleration of point P will be 0 along incline. Now don't say along x-axis here. Then from that AC minus R alpha C equals 0 or AC equal to R alpha C. No slipping condition. Let's write the equation. Mg sine theta minus F equal to MAC. Then F into R is equal to IC into alpha C. Condition for no slipping, AC equal to R alpha C. Let's solve for friction and acceleration. So alpha C, what you can write it as? AC by R. So therefore, what is it? Further F is equal to IC AC by R square. That I'll substitute in the first equation. Mg sine theta IC AC R square equal to MAC. So what is the acceleration is equal to mg sine theta R square is equal to IC plus MR square. I think this already we know. If you apply force at the center of mass, what is the expression for acceleration? Let's focus on the friction. Let's get into the friction here. So let me substitute directly value of AC here. That's all, no, nothing to do in this equation. If I substitute this here, so what is the expression for F will be IC by R square is equal to mg sine theta R square by IC plus MR square. What will get eliminated? Mg sine theta R square get eliminated, so 1 plus MR square by IC. This is something very important. What are other forces acting? Mg cos theta. Normal contact. Yes, they'll be acting. Don't think that they should not act here. They will act as usual. Then what is my question further next? Like, what is the velocity of that rigid body when it reaches the bottom of incline? When it reaches here, what is the velocity of that? So we brought expression for F. This already we know it. I say that I want this velocity of center of mass and also the angular velocity. How much of height it has descended? Let it descend an height h. So this is the expression for friction, everything. Okay, how to get that h? I'll directly apply conservation of mechanical. You should ask this question. So like, can you really apply such things here? Because friction is acting. What is the net work done by friction, rolling friction? What is this? This F is a rolling friction. What is the net work done by rolling friction? Will be 0, as usual here also. So decrease in potential energy, mgh should be equal to increase in translational kinetic energy plus rotational kinetic energy. For pure rolling, you can also write V equal to R omega, and also you can write XC R phi. Theta is angle of inclination. Net work done by friction. Friction does negative translational work. and positive rotation work. Net work done by friction will be 0. Therefore, I'm able to apply the condition of mechanical energy. So substituting this, what is omega? Omega is will be V by R O squared. Solve this, you'll get expression for V. Net work done no. Different rigid bodies I'll release. Let me release the disk. Friction acting, will it be same? No. Let me release the ring. The friction it will be different. So the rolling friction, shall I say, depends upon what? Depends also on the distribution of mass. Let me release a ring disk. All are of mass m and radius r. If I release them, the friction acting, rolling friction acting on the disk and the ring, will it be same? The answer is no. It also depends on what distribution of mass. Look at the acceleration. For different rigid bodies, what will happen? The acceleration of center will be different. And what will happen to velocity also? Will all the rigid bodies will acquire same speed when they reach bottom of incline? No. Solve for this, you'll get expression for V. So let me write it. This will be 2 mgh is equal to m plus ic r square v square. So what is the expression for V? V will be 2 mgh r square by mr square plus ic. Well, all the spheres will have same speed when they reach bottom of incline? No. I'll release the ring and the disk. Both will have same speed. Both are having same mass, same radius. Both will have same speed when they reach bottom of incline. The answer is no. Because M, R, G, H all are same, but IC will be different for different rigid bodies. Getting the idea now? Now what about the time taken by them? Acceleration is different. Distance covered is same. Then you write it S equal to half AT square. AC is different, but distance covered is same. Then time taken will be different here. So what you should do now? So if you release the ring and disk, whatever the time taken by them to reach the bottom of incline will be different. You can solve for this. Our next question comes for any value of what should be the minimum value of mu for which slipping occurs? Any condition for mu. The next very important part of the discussion, what we are going to make. For any value of mu, the rigid body will roll here, or only some specific values. What will be the minimum value of mu for which it will have pure rolling? Any conditions will you put it here? Any condition, what should be the minimum value of mu for which rolling occurs, pure rolling occurs? The condition for mu, as I am just trying to introduce here. Now, sir, why you are bringing mu? Already pure rolling is their problem solved. Why we should again think anything new here? This was the basic question. No, the value of, there should be some minimum value of mu is needed. If the mu is less than or greater than, then slipping will occur. Okay, well now we'll focus on that one. So we have expression for friction, no? mg sin theta 1 plus mr square ic. That will take it here now. For any friction, what will happen? What will be the rolling friction basic idea? It should be less than the limiting friction, no? Then we can call it a rolling friction for no slipping. Let me keep this formula in hand. And one very important part, which I'm going to conclude now, just all of you look at here. Let's start for a ring. There's a ring, and we know for moment of inertia for a ring how much? I think I'll take disk. For this moment of inertia, how much? mr square by 2. Then I'm going to release a disk on an inclined plane. For any value of mu, will it have pure rolling? The answer is no. So next question comes, what is the minimum value of mu for which it will have pure rolling? So definitely the friction acting here should be less than limiting friction. Try to notice all the forces which I'm going to show here. Mg sin theta, sorry, mg cos theta, and acceleration of center of mass, AC, and this is alpha c. Already we have discussed everything. Okay, let's come for this one. Now, what should be the for no slipping? What should be the F? F should be less than mu s n, no? And what is in fact n? N minus mg cos theta equal to 0. F should be mu s mg cos theta. Let me substitute this F here, what I brought it. Mg sin theta 1 plus mr square by IC less than mu s mg cos theta. Mg gets eliminated. For a disk, okay, let me write it here. So this should become equal to tan theta by 1 plus mr square by IC less than mu s. That is a very important equation is what I brought it. Okay, after this what to do? Now for a disk, what is IC? mr square by 2. This is a generalized formula. Now let me substitute here. Tan theta by 1 plus no. So finally, what we can write it this one. Tan theta by 3 should be less than mu s. How shall we put it? Mu s should be greater than tan theta by 3. So minimum value, how much? Tan theta by 3. If the quotient of friction between the disk and the inclined plane, if it is tan theta by 3, anything greater than or equal to tan theta by 3, no slipping occurs. If it is less than this, there will be slipping, whatever you do it. This is for what? If you release a disk. No, sir, I'll release a ring. Then will slipping occurs or not will determine the value of mu minimum and the tan theta. So in a numerical, what you should do? They'll be giving you mu s value. They'll be giving you theta. Check it now. Is it mu greater than tan theta by 3 or not? Minimum, no. At least what happened? It should be equal to tan theta by 3. What is theta? Angle of inclination. Same thing, instead of this, let it be a ring. For a ring, what conditions you can write? I think I'll take it out because we are making generalized, no? No. For a ring, what you can write it? No. For a ring, what is IC? mr square by 2. So this will be tan theta 1 plus mr square by mr square. Should be less than mu s. So therefore tan theta by 2 less than mu s. So mu s must be greater than tan theta by 2. What is the minimum value? It's telling if you release a ring on a rough inclined plane, then for no slipping occur, what should be the minimum value of mu? Tan theta by 2. Sir, then then I'll bring a same rigid body. Means I'll take a wooden ring of mass m and radius r. Then I'll bring a what happened wooden disc of mass m and radius r. Then if this particular there's a disc, no, this is for a disc. What will be the requirement of mu minimum? For this what happened tan theta by 3, and for a what happened ring it should be tan theta by 2. I think there's a very strange thing, no? I'm just comparing body. If I just ended up with only one generalized case, you might have thought, okay, fine. But for different rigid bodies, what happened if you release it on a rough inclined plane, what happened? You should determine. So here what happened? Both the rigid bodies are having same mass and radius r, but because of moment of inertia are different, the value of mu needed will be different. There's a minimum coefficient of friction between the rigid body and the inclined plane is needed for this one. Sir, for no slipping, this is a thing. I think I should write here for no slipping. So somebody is asking, sir, why this condition for no slipping? And again, this is for no slipping. If it is less than this value, if the mu is less than this mu minimum, then what happens? You release the rigid body, it will undergo slipping. It will undergo slipping means then what conditions I should assume, sir? What conditions I assume? The friction you should not write small f, you should write fk. Able to understand the basic necessity of this? I'll draw the diagram for that also. If a mu, this is very important part of the discussion which we are making again. Let me do for the ring only. So I have a ring. What is the minimum value of tan theta by 2? Oh. Let's continue the problem. So I do have a ring. I think anybody can understand, just you should have that basic ideas clearly. Not these are very big things. No, this is a radius r. Now I'm going to write the value of mu s is how much. So what is the minimum? How much needed? Tan theta by 2. If I write this is tan theta by 4, tell me what is the problem? It's a ring. How much minimum needed? Tan theta by 2. But how much mu is mu s is tan theta by 4. So definitely the friction acting will be kinetic. Then what are other forces? Mg sine theta. Not a rolling friction. Sir, will there be torque? Yes, there will be torque. What's wrong in that one? Torque will act. Then what are the equations? Mg sine theta minus Fk, you write it. MAC. Then torque by friction Fk into R is equal to mr square into alpha. There's a ring, no? Then you cannot write AC equal to R alpha C. Any reason for that? Slipping occurs. Forward slipping or backward slipping? Calculate, you know Fk. So you know Fk. So calculate AC. You know Fk, calculate alpha C. Check it here. AC less than R alpha C or greater than R alpha C. Able to understand the core idea? So why sir, why not rolling friction? Kinetic friction is acting. Sir, why no rolling friction? Because this condition is not satisfied. So what is at least the minimum? Minimum how much it should be? Tan theta by 2. Tan theta by 4 is what? Less than tan theta by 2. So the mu is in fact here is less than mu minimum. So therefore slipping occurs. If mu greater than mu minimum, rolling will occur. Able to understand this one? Minimum is what you have to bring into picture here. So therefore, when you release a rigid body on a rough surface, what is the first thing, whether slipping will occur or not? Who will decide? The mu and theta relationship. Like that, what you should remember for what? I think these formulas in exams you can't derive. A student must have this idea. For a solid sphere, for a hollow sphere, for a ring, for a disc. I think these are the four rigid bodies which are very popular. For all that, you remember this formula so that you can immediately get into the problem. ring tan theta by 3, this tan theta by 2, then solid sphere also check it, hollow sphere also you check it. For rigid bodies, you must remember that mu minimum. Sir, if mu is greater than tan theta by 2, greater than tan theta by 2, anybody suggest mu s 2 tan theta by 3, shall we make it? If mu is equal to mu 2 tan theta by 3, then what will happen? Next year, let me conclude here so that it will be easy for you. This is a ring. So now this is theta. What is the value of mu? Mu is 2 tan theta by 3. Is it greater than mu minimum? Yes, it is greater than mu minimum. What friction will act here? Rolling friction. Small ideas, nothing big, small ideas. You must have a patience to what? To analyze things. That's all. No concepts are there, nothing. There's a ring, no? Yeah. No. What are the forces that will be acting here? Mg sine theta. Then mg cos theta, normal contact acting, so there should be kinetic. No, the condition is satisfied. Mu is in fact, so then center of mass will have, and the friction will set up a torque. What is this? Rolling friction. So then what are the equations? Mg sine theta minus f equal to mac. F into r equal to is alpha. Then ac equal to r alpha c. Strictly what is this friction? Rolling friction. Then ac is equal to pure rolling. No. So slipping will occur or not will determine the condition of mu. I think got it in a very simplified way. I'm just put everything in front of you. Sir, can I apply Work-Kenji theorem here? No. Net work done by friction will be non-zero. Very important part here. Net work done by friction is non-zero. Then how to calculate the velocity of the ring when it reaches bottom of incline? I want this velocity v1 and omega 1. Can you apply? Net work done by friction is non-zero. Sir, you only said 0. If it were what? Rolling friction. Now it's what? Kinetic friction. Net work done will be non-zero. How to calculate V1, V2? We can't find out. No, you know acceleration. If you know acceleration, can't you find out V1? What is the expression for V1? V1 equal to 2AC into X. Let X be the distance covered from here to here. V square equal to 2X formula. Then how to calculate the omega? You know torque alpha C. Omega 1 equal to what? Alpha C into angular displacement, you call it. Or if you know time, from the time, yes, you can apply equations of motion and work out. Nothing that you can't find out the velocities. No, you can find out. Individually calculate velocity, individually calculate the angular velocity. But you can't write V1 equal to what? R omega 1. V1 is in fact not equal to R omega 1. The same equations will govern here. Because slipping occurs. Okay, I think I took extra 5 minutes time. We'll wind up the class here only. Today evening I'll take class because plenty of numericals I have to discuss. Not only few, plenty of ideas are there. Evening I'll intimate time.